Welcome back to the Deep Dive. Today, we're really tearing apart the blueprints of the modern internet.
That's right.
Our mission is to figure out how these massive online services, the ones juggling, billions of requests daily, manage all that data without blinking.
Yeah, without ever going down.
Exactly. So we're designing a distributed, highly scalable key value store pretty much from the ground up.
And this isn't just like abstract theory. We're pulling out the core engineering choices, the actual technical bits that make systems like Amazon Dynamo work.
The engine behind Amazon Shop, right?
To very one. And also Apache Cassandra, which gets used all over for huge data sets. So for you listening, this is kind of the shortcut to understanding the complex machinery.
Vector clocks, Merkle trees, all that stuff.
The things that make these planet-scale databases actually possible.
Okay, let's unpack this. First things first, what exactly are we building here? Because the basic idea seems almost too simple. Hashtag, tag, IOA. Introduction and establishing the design scope.
Well, at its core, a key value store, or KVS, it's maybe the simplest non-relational database you can think of.
Okay.
You've got a unique identifier that's the key, and paired with it, you have its data, the value.
Key value pair, that's the fundamental piece.
That's the atom of the system, yeah.
And the key has to be unique. That's the critical part. It's like the address label.
Exactly. You need that specific key to get the value back. And performance matters here.
How so?
Well, the source material is pretty clear. Shorter keys just work better.
Less data to handle.
Less storage overhead, faster hashing, faster comparisons inside the system. Keys can be readable text, like last love Jedinit.
Or just a jumble of characters, like a hash.
Right, like 253DDEC4. Both work.
Okay, so unique key. What about the value? What can that be?
That's the interesting part. The KVS itself, it doesn't really care. The value is just a blob, an opaque object.
So anything goes.
Pretty much a simple string, maybe a JSON object, a list, some complex thing you've serialized. The database just holds it. That's way more flexible than, say, rigid relational tables.
And that simplicity, that's where the speed comes from, like Memcache or Redis.
Exactly. Or Amazon Dynamo. They don't mess around with relationships, joins, complex queries. It's just two main jobs.
Couldn't get.
Put key, value, to store or update data. Get key to fetch it. That's basically the whole conversation you have with the database.
Okay, simple operations, but our design mission, our listeners' requirements,
Yeah.
they're pretty demanding.
Oh, yeah. We need to handle big data, so high scalability is a must.
And the pairs themselves are small, under 10 KB, but the big ones are availability and latency.
High availability and low latency. The system needs to be fast and always responsive.
And maybe the most telling requirement, tunable consistency.
Yes. That signals our whole approach. We're not aiming for perfect instant agreement across all data copies.
We want flexibility,
Sure.
which I guess means we're leaning towards eventual consistency.
Precisely. We're choosing to accept that data might be slightly out of sync sometimes in order to keep the system fast and resilient.
Because there's always a trade-off, right? No perfect design.
Never. You're always balancing things. Read speed, write speed, memory use, and that core tension between consistency and availability.
We're basically saying uptime and speed are more critical for this system than having every single node perfectly identical at every microsecond.
Exactly. Which naturally leads to the question, why bother distributing at all?
Right. If the data was small enough, couldn't we just stick it all in memory on one machine? Like a hash table? That'd be super fast.
Blazing fast, but only until your data grows bigger than that one machine's memory.
You can compress data, maybe push less used stuff to disk.
Sure, you can optimize, but a single server hits limits. Memory limits, CPU limits, network limits. If you're talking big data petabytes and tons of transactions, one box just won't cut it.
Plus, it's a single point of failure. Server dies, system dies.
Yep.
So, conclusion. We have to build a distributed key value store, sometimes called a distributed hash table. We need to spread those keys and values across lots of machines.
And the second we connect those machines over a network, things get complicated.
That's where the philosophy comes in. You immediately run into the CAP theorem.
CAP. The fundamental law of distributed systems. You can pick 2 guarantees out of 3, but never all 3 simultaneously. Let's break down those 3 pillars.
Okay, first pillar, consistency. This is the ideal world scenario.
Everyone sees the same thing at the same time.
Exactly. Every client, no matter which server node they talk to, gets the exact same data. A single, unified view of the truth across the whole system.
Got it. Pillar 2.
Availability. A. This just means the system answers you. Every request a client sends gets some kind of response, a read or a write acknowledgement.
Even if some servers are down.
Even if some nodes are offline or struggling, the system is always up, always ready to serve.
And the third pillar, the one that forces the trade-off. Partition tolerance, P. This is the big one. A partition is basically a network break.
Like servers in one data center can't talk to servers in another.
Precisely, or even within the same rack, partition tolerance means the system keeps working despite these communication breakdowns.
Okay, CAP. Now the kicker is P, right? Network failures,
Yeah.
they just happen.
They're unavoidable in any real distributed system. Cables fail, routers glitch, configurations get messed up. It's a fact of life.
So partition tolerance isn't really optional. You have to design for it if you want a robust system.
Absolutely. P is mandatory, which immediately rules out CA systems' consistency and availability without partition tolerance. They just don't exist in the real world, not reliably anyway.
So we're forced to choose CP or AP.
Consistency plus partition tolerance or availability plus partition tolerance. Which do you sacrifice? Consistency or availability?
Data correctness or system uptime. Let's use that example. 3 servers, N1, N2, N3. N3 gets cut off from the others. A client tries to write something to N1.
Okay. If we chose a CP system prioritizing consistency, what happens?
Well, the system knows N1 can't tell N3 about the write. That would make the data inconsistent.
Right. So to maintain consistency.
It has to block the write on N1. It sacrifices availability to prevent inconsistency.
Think banking systems. You cannot show the wrong balance. Better to say, sorry, try again later, than to process a transaction that might vanish or be wrong.
User gets annoyed, but the data stays correct.
Exactly. No, flip it. What if we chose an AP system prioritizing availability? Same scenario. N3 is partitioned, write comes to N1.
The AP system says, sure, go ahead. It lets N1 accept the write, even knowing N3 won't get it immediately.
The system stays up, keeps taking requests, high availability achieved.
But if another client happens to read from N3 before the network fixes itself.
They get old, stale data. You sacrifice strict, immediate consistency.
Okay, so for our design goals, high availability, low latency, big data access last, the choice seems clear.
It has to be AP. We'd rather occasionally show a slightly out-of-date product recommendation or maybe an older comment than just fail the request entirely.
We accept eventual consistency.
We accept it, but that philosophical choice means we now have a whole bunch of technical problems to solve. How do we manage those inconsistencies we just accepted?
Right, but before we get into fixing inconsistencies, we need to actually spread the data out in the first place.
Right.
Efficiently. Okay, so distributing data. Big challenges here. 1, how do you spread it evenly across potentially thousands of servers?
And 2, how do you add or remove servers without causing a massive data reshuffle? Moving petabytes around is not ideal.
Yeah, that sounds like a system killer. What about simple hashing, like take the keys hashed, divide by the number of servers?
That's the naive approach, and it breaks badly. Hash key, MODN, add just one new server, changing n to n+1, and suddenly almost every key maps to a different server.
Oh, wow. Total data migration.
An avalanche effect, yeah. Grinds everything to a halt. That's why systems like Dynamo and Cassandra use something much smarter. Consistent hashing.
Consistent hashing. How does that work? Is it the ring thing?
Exactly. Imagine a conceptual circle, or ring. The hash values wrap around. First, you hash your server IDs, maybe based on their IP addresses or assigned names, and place them on this ring.
Okay, servers are points on the circle.
Then you take your data key, hash it using the same hash function, and place it on the ring, too.
So keys also land somewhere on the circle.
Right. Now, to figure out which server stores that key, you start at the key's position on the ring and walk clockwise.
Until you hit a server.
The very first server you encounter moving clockwise owns that key. That's its primary home.
Ah, okay. How does that help with adding or removing servers?
It's elegant. Let's say server S5 fails and you remove it from the ring. Which keys need to move?
Only the keys that were landing between S4, the server before S5, and S5 itself, right? They now need to continue clockwise.
Until they hit S6, the next server after S5. So only the data owned by the failed S5 gets redistributed, and only to its immediate clockwise neighbor.
Not the entire data set, just one slice moves.
Exactly. Same if you add a new server, say S8, between S5 and S6.
No.
It just takes responsibility for the keys that fall directly before it on the ring, keys that previously belonged to S6.
Localized changes. That makes scaling much smoother.
That's the key to fluid scaling. Servers can join or leave based on load, and the data movement is minimal.
The sources mentioned other benefits too. Like heterogeneity.
Right, heterogeneity. Not all servers are equal. If you have a beefy new machine with twice the RAM and CPU,
You want it to do more work.
you don't want it just taking one spot on the ring. So you assign it multiple virtual nodes. Maybe it appears at 3 different points on the ring.
So it effectively gets responsible for 3 slices of the data.
Proportionally more data, yeah. Better resource use.
Okay. Consistent hashing tells us where the primary copy lives.
Yeah,
But we need high availability. That means copies, right? Replication.
absolutely. Data needs to be replicated asynchronously across n servers. N is a number you configure.
Usually like 3 or 5.
Typically, yeah. Let's say n3. We want 3 copies total. We use the consistent hashing ring again. How? Find the first server for the key, walking clockwise. That's replica 1. Then just keep walking clockwise around the ring.
And pick the next 2 unique servers you hit.
Exactly. If Keyleo maps to S1 and N3, you store copies on S1, S2, and S3, assuming they are distinct servers.
Makes sense. But where should S1, S2, and S3 physically be?
Crucial point. For real reliability, the sources stress this, replicas must be placed in distinct data centers.
Not just different racks in the same building.
Nope. Think bigger failures, power outage to the whole building, network cut to the area, earthquake, flood.
If all 3 replicas are in the same place, they all die together.
You lose all your data, so you spread them geographically. S1 in Virginia, S2 in Oregon, S3 in Dublin, for example. That protects against those large-scale common failure points.
That's how you get true high availability, even during major disasters. Hashtag tag 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 5e, tunable consistency and conflict resolution.
Okay, so data is partitioned using consistent hashing and replicated across n nodes in different locations. Now we hit the consequence of our AP choice.
Right, we accepted eventual consistency. How do we manage syncing those n replicas? And what happens when they inevitably get out of sync?
The synchronization mechanism is called quorum consensus. It's defined by 3 letters, N, W, and R.
N, we know.
Yeah.
Total number of replicas, like 3. What are W and R?
W is the write quorum. It's the minimum number of replicas that must confirm they received a write operation before the system tells the client, okay, your write was successful.
And
R is the read quorum. The minimum number of replicas that must respond to a read request before the system returns the data to the client.
Who manages this? Is there a central controller?
No central controller overall, but for each client request, one node acts as the coordinator. It's like a temporary traffic cop for that specific operation.
Okay, so let's say N3. What happens if we set W1?
Coordinator gets a write request. It sends it to all 3 replicas, S1, S2, S3. But with W1, it only needs to wait for the fastest one to reply. Got it.
And then it tells the client done, immediately.
Pretty much. Super fast write operation for the client.
But the other 2 replicas might still be processing it. Or maybe one even failed to get it.
Exactly. Speed comes at the cost of immediate consistency. Same for R1. You ask for data, the coordinator asks all 3 replicas, but only waits for the fastest one to respond.
And that fastest one might have slightly older data.
It might. So W1 or R1 gives you speed, but potentially stale reads or slow propagation of writes.
What if W or R is greater than 1, like W2?
Now the coordinator has to wait for acknowledgments from 2 replicas before confirming the write.
Which means waiting for the slower of those 2.
Right, so the operation takes longer, limited by the slowest required replica. But your consistency guarantee goes way up.
And there's that formula, right, for guaranteeing strong consistency.
The magic quorum math. If W plus Rn, strong consistency is guaranteed.
W plus R is greater than N. Why does that work?
Think about it with N3. If you need W2 confirmations for a write, and R2 responses for a read.
2 plus 2, which is greater than N3.
Exactly. So the set of nodes you read from, R2, must overlap by at least 1 node with the set of nodes you wrote to. There's no way to pick 2 nodes for the read and 2 nodes for the write from a pool of 3 without having at least 1 in common.
So you're guaranteed to read from at least 1 node that has the latest successful write. Clever.
It is. But again, for our design, we chose high availability and low latency. Setting W2 and R2 forces us to wait for 2 nodes, slowing things down.
So AP systems often use, N3, W1, R1, or maybe RN?
Configurations like that, yeah. Or maybe W1, R2. You tune W and R based on whether reads or writes are more critical for that specific piece of data and how much consistency you can afford to trade for speed.
Which loops us back to those consistency models. We avoided strong consistency because it often blocks things.
Right, that's more the CP world. We're in the AP world, which means eventual consistency.
Meaning things will eventually catch up.
It's a type of weak consistency. It promises that if things calm down, if there are no new writes for a while, all the updates will eventually propagate, and all n replicas will converge to the same value.
Systems like Dynamo and Cassandra live here. They allow writes to happen, even if not all nodes agree instantly.
But that leads directly to the biggest headache, conflicts.
Okay, let's walk through this. If server A updates data item D, and server B updates the same D at roughly the same time, what happens?
Because we're not strictly coordinating or blocking, both writes might succeed locally on different replicas. We don't have a clean overwrite. We have two different versions of D existing simultaneously. They're called siblings.
Parallel universes for the data. How does the system even know this happened?
That's where vector clocks come in. It's a bit of metadata attached to the data item itself.
Okay, what does it look like?
It's basically a list of pairs. Server ID, version number. It tracks the history of writes across different servers.
Let's trace an example. Client writes version D1, handled by server SexX.
Simple start. The vector clock is just D1, SX1, SX handled version 1.
Okay, now the client reads D1, updates it to D2, writes it back to the same server, SX.
Easy update. D2 clearly comes after D1. SX just increments its counter in the clock. D2, SX2.
All right, now the messy part. Two clients read D2 concurrently. Client A updates it to D3 and writes it to a different server, Psi.
Okay, so Psi handled this right. It increments its counter or adds itself, but the history from SX is still there. The clock for D3 becomes D3, SX, 2, Psi, 1.
Got it. Meanwhile, client B took the same original D2, updated it to D4, and wrote that to a third server, SX.
So similarly, S increments its counter. The clock for D4 is D4, SX, to DS1.
Now we have D3 and D4 floating around. What happens when someone tries to read that key?
The coordinator node, doing its job, might fetch both versions, D3 and D4, from different replicas. It then looks at their vector clocks. How does it compare them? It checks for ancestry. Version X is an ancestor of version Y if every server version pair in X's clock is less than or equal to the corresponding pair in Y's clock.
Okay, let's compare D3 and D4. SX is 2 in both, but D3 has SY1, which isn't D4, and D4 has SZ1, which isn't in D3.
Exactly. Neither clock's values are all less than or equal to the others. Neither one is a clear ancestor of the other.
So they're siblings. Parallel versions.
Detected as siblings, a conflict exists. The system itself usually can't automatically figure out how to merge, say, name John San Francisco and name John New York.
So what does it do?
It punts. It sends both versions, D3 and D4, along with their vector clocks, back to the application client that made the read request.
Whoa. So the database says, here's the mess, you figure it out.
Pretty much. The application layer, the client code, now has to contain the business logic to reconcile these conflicts. It needs to decide how to merge D3 and D4 into a sensible new version. Let's call it D5.
So the application merges John San Francisco and John New York somehow, maybe based on timestamps or user preference, into just John.
Or maybe it keeps both, whatever the application logic dictates. Then the client writes the newly merged version D5 back to the database.
And what happens to the vector clock for D5?
When D5 is written, say it's handled by server SexX again, the new clock incorporates the history from both parents, D3 and D4, and increments the counter for the server handling the merge write. So it might look like D5, SX3, Psi 1, S1.
So the clock now reflects that D5 resolved the conflict between the branches starting at Psi and SES.
Precisely. It unifies the divergent histories.
That's powerful, but wow, that puts a lot of burden on the application developer. They have to anticipate all possible conflicts.
It's a significant shift in complexity, absolutely. And there's another potential issue. Those vector clocks can grow, right? If a key gets updated by many different servers frequently.
The list of server version pairs could get really long.
It could. The sources mention you can potentially cap the size, maybe by removing the oldest pairs after a certain threshold.
But that might lose some history. Affect conflict detection.
There's a small risk, yeah. But interestingly, the original Amazon Dynamo paper mentioned they hadn't actually hit this limit in production. So for many use cases, the growth might be manageable. Hashtag V. Handling failures and system stability.
Okay, we've dealt with consistency, trade-offs, and conflicts. Now let's talk about actual servers just failing. In a huge system, nodes must be going down all the time.
It's not an exception, it's normal operation. You absolutely need fast, reliable failure detection.
Can't you just have every server ping every other server constantly?
Not really feasible at scale. Imagine thousands of nodes. All-to-all pinging creates n-squared traffic. It's overwhelming. Centralized monitoring also creates bottlenecks and single points of failure for detection itself.
So we need something decentralized,
Yeah.
like gossip.
Exactly. The gossip protocol is perfect for this. It spreads information probabilistically, like rumors spreading through a crowd.
How's it work for failure detection?
Each node keeps a local list of other nodes it knows about. This list includes the other node's ID and, crucially, its heartbeat counter.
Heartbeat counter, like a version number for being alive.
Sort of, yeah. Each node periodically increments its own heartbeat counter. Then, periodically, maybe every second, it picks a few random other nodes from its list.
And tells them.
Hey, my heartbeat is now X. Oh, and by the way, here's the latest heartbeat info I have for nodes Y and Z.
So it passes along its own status, and status updates it heard about others.
Right. The receiving node updates its own list with this newer information. If it hears conflicting info about node Z, it usually trusts the higher heartbeat counter. Then, in its next gossip round, it might pass that updated info along to other random nodes.
Information spreads through the cluster randomly but quickly.
Like gossip. Efficiently, without flooding the network.
So how does this detect a failure?
If a node, say node A, is gossiping around and it keeps hearing that node B's heartbeat counter hasn't increased for a certain amount of time, maybe 10
It
seconds.
starts to suspect node B might be down.
Exactly. It might mark B as suspicious. If several nodes independently come to the same conclusion through gossip, they eventually agree to mark node B as officially offline.
And that offline status then gets gossiped around too.
Yep. So coordinators learn quickly not to send requests to node B.
Okay, failure detected via gossip. Now, what if the failure is just temporary, like a server rebooting or a short network blip? We can't just stop serving requests, right? That violates high availability.
Correct. We need mechanisms to handle temporary hiccups gracefully. That's where sloppy quorum and hinted handoff come in.
Sloppy quorum. Sounds messy.
It's about being flexible for availability. Remember our N? WR quorum. Normally, the coordinator sends requests to the specific N nodes dictated by consistent hashing.
Right, S1, S2, S3 for key 0.
But what if the coordinator knows, via gossip, that S2 is currently down? A strict quorum would fail if WR required S2.
So sloppy quorum says,
It says, okay, S2 is down. Just ignore the strict placement for a moment. Find the first W, or R, healthy servers available on the ring, walking clockwise from the target key, even if they aren't the original N.
so maybe it picks S1, S3, and S4 instead of S1, S2, S3?
Exactly. It temporarily relaxes the rules to meet the quorum count with available nodes, keeping the operation alive. Availability over strictness.
But wait, if S4 took a write that was really meant for S2, what happens to that data?
That's hinted handoff. When S4 accepts that write under sloppy quorum, it knows, because the coordinator tells it, that this write was originally intended for S2.
So it makes a note.
It stores the data, but also stores a hint, basically metadata saying this belongs to S2. It effectively queues up the data destined for the temporarily unavailable node.
And when S2 comes back online,
Gossip spreads the word. S2 is back.
Huh.
When S4 hears this, it checks its hints. I had this data for S2. It then hands off that queued data back to the recovered S2.
so the data eventually gets to its rightful home. Consistency is restored, eventually.
Exactly. Sloppy quorum plus hinted handoff, high availability during temporary failures, plus eventual consistency maintained.
Okay, that handles temporary glitches. What about permanent failures? Disk dies, server melts down, gone forever. How do we ensure the replicas stay in sync then and replace the lost data permanently?
We need a background process constantly checking for inconsistencies between replicas and repairing them. This is generally called an anti-entropy protocol.
Anti-entropy. Fighting against disorder. How does it work? Naively, you could just compare every key value pair between two replicas.
You could, but imagine comparing petabytes of data key by key across the network. Insanely slow and expensive.
Yeah, impractical. Is there a checksum approach? Hash the whole data set on each replica and compare hashes.
Better, but still limited. If the top-level hashes mismatch, you know something is different, but you don't know what or where. You'd still have to drill down, maybe comparing hashes of large chunks than smaller chunks.
Which sounds like a tree.
Precisely. The efficient solution is the Merkle tree, or hash tree.
Okay, how do you build a Merkle tree for a replica's data?
First, you divide the entire range of keys that replica is responsible for into many smaller buckets or ranges. Let's say you break 1 billion keys into maybe 1 million buckets.
Step 1, buckets.
Step 2, for each bucket, calculate a hash of all the key value pairs within it. Just hash the contents of that specific bucket.
Step 3, create a leaf node in your tree for each bucket. The value of that leaf node is the hash you just calculated for its bucket.
Step 4. Build the tree upwards. Take pairs of adjacent leaf nodes, bucket hashes, hash them together to create a parent node hash. Keep doing this, hashing pairs of child hashes to create parent hashes, moving up level by level.
Until you reach the very top, a single hash representing the entire data set on that replica.
The single root hash, that's your Merkle tree.
Okay, now how do two replicas use their trees to sync up efficiently?
They start simple. They just compare their root hashes.
If the root hashes match.
They're done. The replicas are identical with extremely high probability. Zero data needs to be transferred. Super efficient.
But if the root hashes differ,
Now we know there's an inconsistency somewhere. But instead of scanning everything, we traverse down the tree. The nodes compare the hashes of their left children.
if the left children's hashes match,
Then the entire left half of the key space is identical. Ignore it. The difference must be in the right half. So compare the right children's hashes.
and if those differ,
Keep going down that branch. Compare their children, and so on. You recursively descend the tree, only exploring the branches where the hashes don't match.
until you reach a leaf node whose hash differs.
Exactly. Now you've pinpointed the specific bucket that contains the inconsistent data.
So you only need to transfer the actual key value data for that specific bucket, not the whole replica.
Precisely. The amount of data transferred is proportional only to the differences between the replicas, not the total size. It's incredibly efficient for finding and fixing inconsistencies.
That's the magic of Merkle trees in anti-entropy. Handles permanent failures and keeps replicas converging over time. Hashtag tag 6, system architecture and data flow. Okay, we've got the CAP, philosophy, AP, distribution, consistent hashing, replication, and coffee's data centers, consistency management, quorum, vector clocks, and failure handling, gossip, sloppy quorum, Merkle trees. Let's zoom out and see the whole system architecture.
The big picture is fundamentally decentralized. That's key. Every node in the cluster is a peer, capable of handling any task.
No single master node.
No master, no single point of failure. That's a huge advantage over older designs. Clients interact with the system using those two simple API calls we mentioned.
Get key and put key, value.
Right. When a client makes a request, it doesn't necessarily know which physical nodes hold the data. It talks to any node in the cluster, which then acts as the coordinator for that request.
And the coordinator knows the cluster layout, thanks to gossip.
Exactly. The coordinator uses its knowledge of the ring from consistent hashing and node health from gossip to figure out which N replicas are responsible for the key.
And then it manages the W or R quorum communication with those replicas.
Yep. It's a stateless proxy for the client interaction. Now, let's look at what happens inside a replica node when it actually gets a write request. The data flow is critical for performance and durability. Cassandra's architecture is a good model here.
Okay, the right path. A replica node receives a put key value request from the coordinator. What's the absolute first thing it does?
Durability first. Before acknowledging anything, it writes the request to an append-only commit log file on disk.
Append only, so just adding to the end.
Fast. Very fast sequential disk write. This is the safety net. If the server crashes immediately after this, when it restarts, it can replay the commit log to recover any writes that didn't make it further.
Okay, log for safety. What next? Speed.
Speed. The data is then written into an in-memory data structure, often called a memory cache or mem table.
So it's immediately available for reads from memory.
Right. Super fast access if someone reads that key right away.
But memory is limited. What happens when the mem table fills up?
When it hits a certain size threshold, or maybe after a certain time period, the entire contents of the in-memory mem table are flushed to disk.
As what?
As a new immutable file called an SS table, a sorted string table.
Sorted. Why sorted?
Sorted by key. This makes reading from them very efficient later, even though they're on slower disk. And immutable means they are never modified once written.
So new writes or updates just create new S tables. You don't edit old ones.
Correct. Over time, you accumulate lots of these SS table files on disk. There's a separate background process called compaction that merges smaller SS tables into bigger ones, cleans up deleted data, and keeps read performance reasonable.
Okay, that's the right path. Commit log,
Yeah.
disk, safety, memory speed, SS table flush, disk, persistence. What about the read path?
Client sends get key to coordinator. Coordinator sends it to relevant replicas based on our quorum. A replica receives the read request, fastest path.
Check the memory cache, the mem table.
Always check memory first. If the key is found there, boom, return the value. Millisecond latency.
But if it's not in memory, could be in any one of those dozens, maybe hundreds of SS-stable files on disk.
Could be. And scanning every single SS stable file on disk for the key would be terribly slow. Disk seeks are expensive.
So how do you avoid that? How do you know which SS stables to even look in?
This is where Bloom filters come in. They are a fantastic probabilistic optimization.
Probabilistic, meaning not always right.
Sort of. For each SS stable file on disk, the system also keeps a corresponding Bloom filter in memory. A Bloom filter is very small, much smaller than the SS stable data itself.
What does it do?
When you need to check if a key might be in a particular SS stable, you ask its Bloom filter first. The Bloom filter can tell you one of two things very quickly.
What?
One, this key is definitely not in this SS stable.
Okay, so you can skip reading that file entirely. Saves a disk read.
Huge saving. Or two, this key might be in this SS stable.
Might be, so it could be a false alarm.
Exactly. A Bloom filter never gives a false negative. It never says no when the key is actually there, but it can give a false positive. It can say maybe when the key isn't actually there.
It's okay.
It's usually perfectly acceptable. The chance of a false positive is low if the filter is sized correctly. The cost is just one unnecessary disk read for that SS stable. That's vastly cheaper than reading all the SS stables.
So the read path is check mem table. If not found, check Bloom filters for all SS stables. Identify the S stables that might contain the key. Read only those candidate S stables from disk. Find the key, if it exists. Return the result.
Precisely. The coordinator collects responses based on the read quorum and sends the result back to the client. Hashtag tag a summary and final thought.
Wow, okay. That was quite a journey through the guts of a highly scalable key value store. We basically built a system prioritizing availability and scale.
We really did. Let's quickly recap the main tools we used to get there. For scaling, handling lots of data and servers.
Consistent hashing. Distributes the load, minimizes data movement when servers join or leave.
For high availability and reliability, making sure it stays up and data isn't lost.
Data replication across different data centers using that configurable N, plus the quorum consensus, W and R, for tuning consistency, and sloppy quorum with hinted handoff to handle temporary failures gracefully.
Right. Durability, making sure writes stick.
That was the commit log first, then the memtable cache eventually flushed to immutable SS stables on disk.
Managing inconsistency, the result of our AP choice.
Vector clocks to detect concurrent writes and conflicts, leaving reconciliation to the client. And for background syncing and fixing permanent failures, the anti-entropy process using Merkle trees.
And finally, speeding up reads.
Avoiding slow disk scans with Bloom filters.
That's pretty much the toolkit.
So for you listening, the big takeaway is that designing these systems is all about managing complexity and making very deliberate trade-offs, especially that CAP theorem choice.
Yeah, you can't have it all. If you choose AP availability and partition tolerance like we did, you gain uptime and responsiveness, but you buy complexity elsewhere.
You have to build in all these other mechanisms, vector clocks, hinted handoff, anti-entropy, to deal with the eventual consistency you accepted.
It shifts the burden. The system stays up, but now you or your client application might have more work to do.
Which leads perfectly into our final provocative thought. It's about that conflict resolution we discussed with vector clocks.
Yeah. The D3 versus D4 needing to become D5.
Right. In systems like Dynamo and Cassandra, the database itself doesn't decide how to merge those conflicting versions. It detects the conflict using the vector clock and then hands both versions back to the application client.
The client code has to contain the logic to reconcile the data.
So the question for you to think about is, how does this fundamental shift in responsibility, moving the hardest part of data reconciliation out of the database and into the application logic, change how we even define database management in these massive distributed systems?
Is the database just managing storage and conflict detection, while the application becomes the ultimate arbiter of data truth? Are we managing databases anymore, or are we managing decentralized consensus engines where the client plays a critical role in defining consistency?
Something to chew on next time you hit refresh on a website that feels instantaneous despite handling millions of users. That's the end of our deep dive for today. Thanks for joining us.
Yeah, great discussion. We'll catch you on the next one.